Imagine a giant invisible net cast across the sky, selectively snaring carbon dioxide molecules out of the air. Carbon capture technologies are essentially doing just that, grabbing CO2 from a diffuse mix of gases and then letting it go on command. By using clever swings, changes in temperature, pressure, humidity, or electrical conditions, to turn a CO2-grabbing chemical attraction on and off. Today, we are exploring 4 core CO2 capture methods: temperature swing, pressure swing, moisture swing, and electrochemical swing. Each method is like a different magic trick for trapping carbon from thin air and releasing it in concentrated form. The first and most established method is temperature swing adsorption, or TSA. This is carbon capture in its most conventional form. Use a sorbent that grabs CO2 at one temperature, then heat it up to make it let go. Think of a sponge that soaks up CO2 at room temperature and then wrings itself out when heated. The science is rooted in thermodynamics. Binding CO2 to a sorbent releases heat, an exothermic reaction. So adding heat reverses the reaction and frees the CO2. Amines are the all-star sorbents here. These nitrogen-rich chemicals, think of ammonia derivatives, chemically bind CO2, forming carbaminates or bicarbonates on their surface. In liquid form, like the classic monoethanolamine solutions used since the 1930s, or fixed on solids, like porous filters coated with amines, they have a high selectivity for CO2. They're basically CO2 magnets. Other sorbents for TSA include solid metal organic frameworks, MOFs, and porous zeolites that can fizzy-sorb CO2, stick it by physical attraction. These often have tailored pore sizes that fit CO2 molecules and release them when heated. Heating a sorbent up and cooling it repeatedly is energy-intensive. In a power plant carbon capture, the regeneration heat for amine solvents typically eats up more than 2.3 gigajoules per ton of CO2 captured, a huge energy penalty, though some heat can come from plant steam. For direct air capture, where CO2 is ultra-dilute, temperature swings can be even larger and require more energy per ton captured. Despite these challenges, TSA remains a workhorse because it's simple and robust. TSA systems can take the form of packed bed reactors, but modern designs use modular contactors and monoliths for efficiency. For example, Climeworks, a leading DAC company from Switzerland, builds stacked monolithic filter units. Imagine a honeycomb of sorbent-coated surfaces. They suck ambient air with fans, CO2 sticks to the filter, then they seal the unit and heat it with steam to 100 degrees Celsius to release pure CO2. Their Orca plant in Iceland has a capacity of 4,000 tons of CO2 per year, using low-grade waste heat for regeneration. Right now, this costs on the order of hundreds of dollars per ton. Climeworks' commercial removal service has been reported at around $600 plus per ton, and only early customers pay that. But with scale and better sorbents, they aim to drop below $100 per ton in the future. Another TSA pioneer is Carbon Engineering of Canada, which uses liquid alkali, a potassium hydroxide solution, to capture CO2, then a temperature swing via calcination. They convert the CO2 into limestone pellets and heat them to 900 degrees Celsius in a kiln to release CO2. It's an extreme temperature swing that consumes a lot of energy, but at large scale, their designs are for megaton per year plants. They project costs in the low hundreds per ton with optimized heat recovery. Each approach, solid filters versus liquid loops, has trade-offs, but they both rely on heating a sorbent to harvest CO2.
One big issue with TSA is that heat can wear out the sorbents. Amines can degrade over time. Imagine baking a sponge in the oven repeatedly. Eventually, it falls apart. Companies have improved amine formulations to last thousands of cycles, but high temperatures will always limit lifetime to some extent. The good news is newer solid sorbents and supports, like robust MOFs or binders, plus isothermal process tweaks, are extending lifespans. Some systems operate at moderate temperatures, 60 to 120 degrees Celsius, to be gentler on materials, though that can leave some CO2 unreleased. Overall, TSA is powerful but energy-hungry. Instead of heating the sorbent, we can change the pressure around it to get CO2 on and off. This is pressure swing adsorption, PSA, a technique long used in industry to separate gases. Here, CO2 is captured at higher pressure and released when pressure is lowered, often pulled into vacuum. Gas solubility and adsorption capacity usually increase with pressure. Pack more CO2 molecules in, and the sorbent grabs more. To release, just drop the pressure and the CO2 pops off. In practice, PSA for carbon capture often means pressurizing the gas or pulling a vacuum on the sorbent bed. In fact, in many systems, PSA and TSA are combined. For example, vacuum swing with a mild temperature lift. The basic idea: adsorb CO2 at 1 atmosphere, then evacuate the chamber to, say, 0.1 atmospheres, so the CO2 desorbs. It's like opening a soda bottle. CO2 comes out when pressure drops. PSA shines in situations where compression is easy. For instance, capturing CO2 from a flue gas that's already pressurized, or purifying hydrogen streams. For direct air capture, PSA alone is tough. Compressing huge volumes of air is energy costly. However, a variant called VSA, vacuum swing adsorption, is used. Essentially, ambient air at 1 atmosphere flows over the sorbent to load CO2. Then the vessel is put under vacuum to unload. Many solid sorbent DAC systems use vacuum-assisted desorption. For example, Global Thermostat, recently acquired by Zero Carbon Systems, uses a combination of low heat, 85 degrees Celsius, and vacuum to regenerate an amine-infused carbon sorbent. By coupling thermal and pressure swings, they can get CO2 off at lower temperatures than pure TSA, saving some energy and being gentler on the sorbent. Global Thermostat's units are basically contactors filled with sorbent granules on porous monoliths. After air capture, they apply vacuum and a bit of heat to pull out the CO2. Another company, Carbon Capture Inc., Los Angeles, USA, builds modular DAC machines and solid sorbents to capture CO2. Air goes through, CO2 sticks on the sorbent, then the box is vacuum pumped to collect CO2. Metal organic frameworks, or MOFs, are great here because you can tune them to grab CO2 strongly even at low pressures. Some have open metal sights that act like CO2 Velcro. The challenge is MOFs can be sensitive to moisture and can be expensive, but new generations are more robust. Carbon Capture Inc. planned a large project in Wyoming to capture 5 million tons per year by 2030. But the project hit a wall when carbon capture couldn't secure enough emissions-free electricity. The Wyoming grid is still dominated by coal, and fierce competition from data centers and crypto miners drove up demand for clean energy. PSA systems often use twin-bed or multi-bed setups, so one vessel captures while another regenerates under vacuum in alternating cycles. In cutting-edge designs, we have fluidized beds, where sorbent particles flow like a fluid. Imagine tiny beads that adsorb CO2 in one chamber at higher pressure, then get conveyed to another chamber where pressure is lowered to release CO2, then sent back, a continuous loop. This is essentially what some proposed moving sorbent DAC systems would do. It's complex, but could handle large throughputs of air. Another format is rapid pressure swing in a rotating contactor, which is Svante's approach for capturing CO2 from flue gas. Svante uses a solid sorbent coated on a rotating monolith that cycles between flue gas exposure, adsorption, and vacuum followed by mild heat, desorption, in a 1-minute cycle. They achieve very fast PSA and TSA cycles, enabling compact units for industrial capture. While Svante is focused on point sources like cement plants, they've achieved about 10 to 30 tons of CO2 captured per day in pilots. Their technology is among the most mature for scaled sorbent systems and could be adapted to air in the future. A big advantage of pressure or vacuum swings is avoiding high-temperature Carnot losses. You don't dump heat into the environment. You mostly do mechanical work. However, compressing or evacuating gas has its own energy cost.
For direct air capture, the energy use typically ranges 5 to 10 gigajoules per ton of CO2, similar to thermal systems. The theoretical minimum is only 0.2 gigajoules per ton, approximately 54 kilowatt hours per ton, for extracting CO2 from 0.04% air, but real systems are far less efficient. Pressure swing methods do have an advantage. They operate near room temperature, which can extend sorbent lifetimes compared to high heat cycles. Still, every swing process pays an energy price. You can't beat thermodynamics, only engineer closer to its limits. Now for a more exotic trick, moisture swing. This method leverages something surprising: a sorbent that grabs CO2 when dry and lets go when exposed to humidity. In other words, changing the moisture, water content, in the air triggers CO2 release. This idea was pioneered by Dr. Klaus Lackner. Picture a sort of artificial tree that breathes in CO2 from dry air and exhales it when it rains or when water is applied. The science relies on special ion exchange resins, which are polymers with charged sites. In dry conditions, these resins have affinity for CO2 in the form of carbonate or bicarbonate. But when wet, the presence of water molecules makes the resin prefer to pick up water and release the CO2 as gas. Essentially, dry equals CO2 captured as carbonate salt, wet equals CO2 expelled, salt goes back to bicarbonate and frees CO2. This moisture-driven cycle is unique because it doesn't require heat or vacuum, just humidity changes, which can be done very passively. Ion exchange resins for moisture swing typically have quaternary ammonium groups, positively charged sites that bind CO2 as carbonate anions when dry. When you introduce water, those sites rather bind hydroxide from water, kicking off the CO2. One example material is a resin called polyallylamine bicarbonate. Dry, it forms carbonate with CO2. Wet, it releases. The beauty is the energy input is low grade. You can literally use ambient humidity or rinse the material with a bit of water. No high temperature ovens, no vacuum pumps. Thermodynamically, the energy is supplied by the difference in free energy between dry and humid air, which can be aided by letting water evaporate, which cools and shifts equilibrium. One analysis showed that whether driven by water or heat, the fundamental energy for moisture swing can be very low. In principle, as low as $1 worth of heat per ton CO2 in ideal conditions. A leading company in moisture swing DAC is Carbon Collect, Dublin, Ireland, and Arizona, USA, which has built prototypes of mechanical trees. These are tall columnar devices that host stacks of resin discs. In dry weather, the discs are extended, absorbing CO2 from the passing air. Once saturated, they retract into a chamber where they're sprayed with water or exposed to humid air, releasing the CO2, which is collected, and then the cycle repeats. Carbon Collect's units passively capture CO2 without energy-intensive fans. Wind does the work, and then use a small amount of energy to create humidity and vacuum out the released CO2 in the chamber. They've reported goals of each tree capturing up to a ton of CO2 per day in ideal conditions, at costs potentially below $100 per ton with mass production. Another outfit, Skytree, located in Amsterdam, the Netherlands, is using moisture swing resins for smaller scale CO2 capture, like scrubbing CO2 inside closed environments, e.g. spacecraft, submarines, or even office buildings to improve air quality. Their tech sprang from NASA life support concepts. While not aimed at gigaton removal, Skytree's systems show how versatile moisture swing sorbents can be, even enabling appliances that literally filter your room's air of CO2. Moisture swing is elegant, but has its own issues. The cycle can be slow, waiting for drying and wetting phases. It's also sensitive to climate, works great in arid conditions with big humidity shifts, less so in already humid places, where the resin might always stay a bit wet. Engineering-wise, you need to handle water carefully to avoid mold or material degradation. Still, moisture swing adsorption stands out as a low-energy consumption approach. In the big picture, moisture swing sorbents might complement other methods by working where cheap heat or power isn't available, but sun and dryness are. Imagine deployments in deserts using just the natural swings of day and night humidity. Now let's plug into the future. Electrochemical swing carbon capture. Instead of changing temperature, pressure, or moisture, we apply an electric voltage to coax CO2 in and out. This is like using electricity to tune the chemistry of a sorbent in real time. An analogy: picture a magnet that turns on and off with a flip of a switch, but for CO2. Electrochemical approaches are exciting because they can be isothermal, no heating and cooling cycles, and can potentially be very energy efficient using electricity, which, if renewable, means zero carbon operation. They also avoid thermal damage to sorbents. You're not baking things repeatedly. There are a few flavors of electrochemical CO2 capture. One prominent example is often called Electrochemical Swing Adsorption. In this design, CO2 is captured on the surface of electrodes when a voltage is applied, and released when the voltage is reversed. How? By using redox active materials that change their affinity for CO2 depending on their oxidation state. A groundbreaking example is the use of quinone-based polymer electrodes developed by Verdox, a startup spun from MIT. Quinones are organic molecules that can gain or lose electrons. When you give them electrons, reduce them, they become negatively charged and will bind CO2. In fact, CO2 can react to form a carbonate with them. When you pull those electrons away, oxidize them, they stop binding CO2 and release it. Verdox have commercialized this technology and have shown 7,000 plus charging-discharging cycles for CO2 capture and release without significant capacity loss. Another approach under the electrochemical umbrella is what we'll call electrochemical pH swing, a type of electrochemical redox system that uses electricity to shift pH and thereby release CO2. One type of pH swing process is called electrochemically mediated amine regeneration, or EMAR. Instead of heating an amine solvent to release CO2, EMAR uses a copper-based redox reaction. In an absorber, CO2 reacts with an amine, just like a regular amine scrubber forming a CO2-loaded solution. Then, in an electrochemical cell, a voltage is applied to oxidize a copper electrode, releasing Cu2+ ions into the solution. The Cu2+ ions bind to the amines, kicking out the CO2, because the amine prefers bonding with Cu2+ over holding CO2. The CO2 is thus liberated without adding heat. The rich CO2 gas is collected, and at the cathode, the copper is reduced back to metal, returning the amine to its original form. EMAR can potentially release 80 to 90% of the absorbed CO2 from the solvent, versus about 50% in some thermal swings that avoid high temps, because it's not limited by boiling point or thermal degradation of amine. In other words, by sidestepping heat, we get a more complete regeneration. This concept is being pursued by startups like Mission Zero, London, UK. Mission Zero uses a similar idea. A hydroxide or carbonate solution absorbs CO2, then an electrochemical cell with membranes and electrodes pumps protons or metal ions to acidify and release CO2 on demand, effectively performing the same role as a 900°C calciner, but at room temperature. Their pilot electrochemical unit aims to cut costs and energy dramatically compared to calcining limestone. There are other electrochemical pH swing processes being invented in research labs and commercialized by companies like Repair, among many others. Ocean-based carbon removal technologies utilizing electrolysis or electrodialysis for carbon capture are also based on the principles of pH swing. Examples include Captura, Aquatic, Ebb Carbon, and CO2. There's also research on using capacitive swings. For example, charging a capacitor in contact with salt water to create local pH gradient, which absorbs CO2 as bicarbonate or carbonate ions, and then discharging to release CO2. This is called capacitive CO2 capture. Capacitive systems consume low-energy, environmentally benign materials capable to operate for 100,000 charge-discharge cycles. Companies like Carbovolt Labs in the US and Norma in Europe are commercializing carbon capture with supercapacitors. Yet another angle, using fuel cells. For example, fuel cell energy system feeds flue gas into a special fuel cell. As the cell generates power, it pumps and concentrates CO2 internally, a sort of electrochemical compressor, yielding a CO2 stream as a byproduct. This isn't a swing per se, but it's an electro-driven separation. The big picture is electrochemical swings give us fine control. We can dial in a voltage to target specific reactions and potentially achieve separation with less wasted energy. They're also easily modular and can be scaled by stacking cells, like a battery stack. The downsides? Right now, cost of electrochemical hardware, membranes and electrodes, is high, and some systems suffer from issues like electrode degradation, membrane fouling, or limited lifetimes. If you're following this video till this point, I congratulate you on learning about incredible landscape of carbon capture innovation. From sponges that breathe CO2 when heated, to crystals that trap gas under pressure, to resins that use the rhythm of rain, and electrodes that act like CO2 magnets, human ingenuity is attacking the climate challenge from all angles. Each method has its strengths. Thermal swings are proven at scale, pressure vacuum systems can leverage existing industrial tech, humidity-driven sorbents offer low-energy simplicity, and electrochemical processes promise precision and integration with clean grids. The key classes of sorbents, amines, MOFs, ionic liquids, carbonates, and polymers are like the palette of a painter, with engineers blending them to create systems that meet different needs. Likewise, the formats, whether packed in a monolith, fluidized as pellets, formed into membranes, or stacked to cells, show that there's no one-size-fits-all. Capture solutions will be tailored to applications. We'll see contactors the size of skyscrapers for giant air farms and tiny CO2 filters in smart homes and vehicles. We'll see direct air capture plants next to geothermal fields supplying heat, and offshore DAC on wind turbines supplying power and air contact in one. Startups today are exploring all these combinations, over 50 companies and counting, each bringing a twist. So let's swing into action. The science is here, the challenge is monumental, but the momentum is building. The air that sustains us is worth every effort to protect. On that note, stay curious, stay motivated, and let's clear the skies, one CO2 molecule at a time.